Okay, so today we're talking about 3.4, a library of functions and piecewise defined functions. The first thing we're going to do is go through the library of functions, just talk about each function, the graph of it, so you can, be able to recognize it and know a little bit about that function. So, and then we're going to talk about piecewise defined functions. That's going to be a little bit deeper. We'll talk about its domain, how to find values, and how to graph it in the end. So the first function we're looking at is the identity function. That's just f of x is equal to x. It's just whatever your input is, that returns as your output. So if you put in a 1, you get a 1. You put in a 2, you get a 2. Put in a 3, you get a 3. Put a 0, you get a 0. Put in -4, you get a -4. And that graph is just this diagonal line here. It's also, if you're familiar with what we talked about with lines, it's just a line y equals x is what that line would be. It's increasing. This can change if it was, put a negative on there, so it's f of x is equal to -x. It would change the way that it is going, and it would be a decreasing function like that. So there are things that can happen with these library of functions that can change them, but we're talking about like the base function here. So just keep that in mind as we're going through them. All right. Next is a constant function. That's just f of x is equal to b, or b is a real number. So that's just a basic function of like f of x is equal to 5, right? And it is just a horizontal line. It's going to go across. All the y values are going to be that b value, or in this case, it would be 5 here. And the x values will vary as we traverse along. As a slope of 0, it's just a horizontal line. All right. Next is a square function. We're going to learn some more about the square function when we get to chapter 4. The square function, the f of x is equal to x squared, is the base format. Now, we did talk about quadratic equations, and so it can get a little bit more complicated. You could have ax squared plus bx plus c as a format, and that bx and that c will change it. The a will change it as well, but we're just looking at the base function here. And so you can see it decreases on this left here, it increases on the right here. The base one has that one intercept at the origin. Now, if the graph was shifted down or up, that will change, which you'll see later on. And it squares the x value. So all the y values are going to be positive. Because when you square -1, well, not positive, they won't be negative. Because you square -1, you get a 1. Square 1, you get 1. Square -2, you get 4. Square 0, you get a 0. 0 is not really positive, it's non-negative. So it's all non-negative values that we have here. Now let's talk about the square root function. Notice that the square root function is the square function, just turn on its side. But we do get rid of the other half of that parabola, if you're familiar with that term. We do get rid of that other half, and that's just so we could keep it as a function. And it's the square root of the x will give you the y. So you got 0, 0, 1, 1, 4, 2, 9, 3, and then we'd have 16, 4 over here. And there's not a lot of points to choose from for this. So you want to look at so much of it that are perfect squares. Notice it is increasing. It begins to increase quickly, but then slows down as we go along. And that is the basic thing. Notice that the domain of it starts at 0. So the domain of the square root function starts at 0, and then it goes all the way to positive infinity. All right. So getting a little bit more complex from the square function, we talk about the cube function. So you have f of x is equal to x cubed. Notice the base function has that x and y intercept of 0, 0. It increases along. It's always increasing. It does do a little change in the rate at which it increases near that origin intersection there, but it does continue to increase. The cube root function is basically that cube function just turned on its side. Notice it too has that xy intercept of 0, 0 to origin. It is also increasing, increases very slowly, then it increases very quickly near that origin point, and then it increases very slowly. It just kind of levels off after that. But it is increasing the entire time for the base form of the cube root function, which is this cube root of x. It's a third degree root, if you want to say it a different way. We have the reciprocal function, which is f of x is equal to 1 over x. So it takes in a number like 5. It gives you back the reciprocal of that number, 1 over 5. So you have points like -2, 1/2. And you'd have 2, 1/2 here. You have 1, 1, -1, -1. Those are reciprocals of themselves. If you put in a fraction, it'll give you a whole number. Well, if it's a fraction with a 1 in the numerator. So if you have 1/2, it would output 2. And they don't show it here, but if you put in -1/2, it'll output -2 over here. Notice there are no intercepts. There's nothing crossing the x-axis here, nothing crossing the y-axis here. And what this function does have, which I'll mark here, is what we call horizontal and vertical asymptotes. So as a horizontal asymptote here for the x-axis, as a vertical asymptote here for the y-axis. Now that can shift if the function gets more complex, but it's a line that the curve of the function will not cross. The reciprocal function has that. The reason for the vertical asymptote is because x cannot equal 0. This function, right? It's a domain restriction there. And the reason for the horizontal is because y can't equal 0. And the reason that y can't equal 0 is because there's no way for me to make 1 over some value equal to 0. The only way for a fraction to equal 0 is if its numerator is 0. In this case, the numerator is 1. So this is why we have y cannot equal 0. That gives us the horizontal asymptote, and the domain restriction on x, where x cannot equal 0, gives us the vertical asymptote we have there. And the absolute value function, we talked about absolute value in 1.6. Basically, it takes in a number, makes it non-negative. So if you put in a -5, you get +5. You put in a 5, you still get a +5. You put in a 0, you get a 0. And the graph of that is interesting because if you put in a -1, you're going to get a 1. If you put in a -2, you get a 2. So it has this line on this side, which is, you could think of it as y equals -x on this side. And then on the right-hand side, it is y equals x. So it kind of switches the function up. Boom, boom. And on this side, it's kind of like the identity function. And then on the left-hand side, it's like the negated identity function that we talked about earlier. So it is decreasing until it gets to the origin, and that'll be your xy intercept there, and then it increases away. And I think we got a few more, maybe more. One more function to talk about. And this is a little specialized function. It's called the greatest integer function. They also call it a step function because it looks like steps. Boom, 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 boom. Basically, f of x will return the integer of x, which is the greatest integer less than or equal to x. So here we got some xy points, order pairs here. But basically what it is it's going to be, let's start here. It's going to be 0 until we hit 1. So for all these fractions between 0 and 1, it's still going to be 0 And then exactly when we hit 1, it's going to switch to 1. And then you got 1.1, 1.2, 1.3, 1.4. And then as soon as we get to 1.9 and we go to 2, boom, it's going to jump up to 2. And it's going to repeat that. Boom, 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 boom. So remember, these open circles mean that it's not actually equal to that point. It just goes towards that point. Like it's approaching that value, but then it jumps up boom, to this filled in circle here. All right, so let's talk about piecewise defined functions. I might need to zoom out a little bit here. So piecewise defined functions are exactly what it says in the name. It's a function that is defined in pieces. And those pieces need to be told when to, we need to be told when to use each piece. So piecewise defined functions are functions that have different definitions for different intervals of x values. And so we're going to look at this one. We're going to try to deep dive into this piecewise defined function and then try to graph it. And that should get us through it all. So part A, well, let's walk through this piecewise defined function, what it is. So this one has 3 different definitions, right? Sometimes it's defined as -2x plus 1. Sometimes it's defined as 2, and sometimes it's defined as x squared. Now, depending on the x value, it will use a different definition. So if x is greater than or equal to -3 or less than 1, it uses this definition here. So if we wanted to write that in interval notation, it'd be from -3 to 1. It's going to use that first definition listed at the top. The middle definition says that when x is 1, the function will be 2. So when x is 1, y is 2. So that just gives us a point. And that point is 1, 2. I wrote the word point there because I don't want you to get it confused with the interval notation I wrote above. This is a point. So it's just going to be a dot on our graph, 1, 2. And then the third definition, the bottom one, is when x is greater than 1, it's going to be defined as x squared. So that's for 1 to infinity. It's going to be defined as x squared. So what that tells us, if you recall, kind of when we talked about different types of functions and different types of equations and stuff, it's going to be linear between -3 and 1. It's going to be just a point, which is linear, I guess, when x is 1. And then it's going to be a quadratic. It's going to be a squared function when x is greater than 1. Okay. So let's go ahead. Let's work on part A. So for part A, they want us to find f of -2, f of 1, and f of 2. So f of -2. What we need to do first is determine which piece we will use when x is -2. So we need to go through all these 3 intervals and figure out which one -2 is in. Is -2 greater than 1? No. So it's not going to use that bottom. Is -2 equal to 1? No. So we're not going to use that middle one. Is -2 between -3 and 1, including the -3? Yes, it is. So we're going to use that top definition. So f of -2 is going to equal -2 times -2 plus 1. Negative got a little bad there. I'm going to rewrite that. And so that'll be what? 4 plus 1 is equal to 5. So f of -2 for this piecewise defined function will be 5. All right. Let's talk about f of 1. Now we need to determine what piece we're going to use. X is 1. So which piece allows x to be 1? Well, this one's just for when x is greater than 1. This is when x is just less than 1. But this middle one is just for when x is equal to 1. So that's the one we're going to use. So f of 1 is just going to be 2. And the last part of that one, they want us to find f of 2. what piece are we going to use when x is 2? 2 is not between -3 and 1. 2 is not equal to 1, but 2 is greater than 1. So we're going to use that bottom piece. So that's going to be 2 squared, which will be 4. So f of 2 for the piecewise, this piecewise defined function will be 4. All right. Let's look at part B. So for part B, they want us to determine the domain of this function. Well, remember the domain of a function is all the x values that it's defined for. Nice thing about a piecewise defined function, they tell us those values explicitly. They say it's this definition for these x values, it's this definition for these x values, this definition for these x values. So all we need to do is combine those x values together. And that's why I wrote this here on the side here. So it's defined for -3 to 1, including the -3 and not including the 1. Then it has this point that does include the 1. And then it goes from 1 to infinity. So if we combine those together, and we could do it on a number line, kind of show you. Let's just start at -4. All right. And so if we look at that first grouping, it's from -3 to 1, including the -3. So we're going to put a bracket on the -3. And it's going to go to 1. I'm going to put a parenthesis on the 1 for the time being. All right. Then we're going to include 1 in it, right? Because it's defined when x is equal to 1. So I'm going to get rid of that parenthesis. I'm going to put a bracket. All right. We go to the next piece. It's when x is greater than 1. So that means it's going to be all these values greater than 1, heading off until towards what? Oh, that looks bad. Towards infinity. There we go. And so the domain of this function f is going to be from -3, including the -3, to positive infinity. And we always put a parenthesis on infinities. That'll be our domain. All right. Let's talk about intercepts. So the x-intercept is the more difficult. So let's look at the y-intercept first. So remember, for y-intercepts, that is in our function where x is equal to 0. All we need to do for a piecewise defined function is figure out which piece allows x to be 0. Well, it's not where it's 1. It's not where it's greater than 1. It's going to be this piece right here. So we just got to take that -2x plus 1 piece and let x equal 0 for it. That's going to be -2 times 0 plus 1, which is going to be 1. So our y-intercept is going to be the point 0, 1. One second. There we go. All right, let's talk about our x-intercept. That's the more difficult of the two. For x-intercept, that's where y is equal to 0. Now, unfortunately, we don't know which piece is going to allow y to equal to 0. But we can determine it. Remember that y for our function is the same thing as f of x. So we're trying to see which piece of this has an output that is 0. And so what we're going to do is do each piece. We'll take -2x plus 1, set it equal to 0, oops, and then we'll solve it. So let's subtract 1 from both sides. We get -2x is equal to -1 divided by -2. And we'll get x is equal to 1/2. Now, that means that that piece will hit 0 for y value when x is 1/2. We do have to make sure that x can be 1/2. Is that x value 1/2 between the -3 and the 1? Yes, it is. So this is a good solution. So let's circle that. We have multiple x-intercepts, so we need to keep trucking. We got to keep moving on this. So let's look at the next piece. It's 2. Can 2 equal 0? Our next piece is defined as 2. No, that's not going to happen. We don't really have to go any further because there's nothing I can do to make 2 equal 0. So boom, don't need to worry about that. All right, let's look at x squared equals 0. See if that has a solution. Well, you could do the square root method if you want to. You can also think of this as the zero product property. X times x is equal to 0, and thus that tells us that x is equal to 0. So we do have a point where x squared will equal 0, and that point is where x is equal to 0. And if we look at that, is that allowed within the range that is defined as that one? So it is defined as x squared when x is greater than 1. 0 is not greater than 1. So that is not going to happen. There we go. So that is not allowed for that piece. So the only x-intercept I'm going to have would be the 1, 1/2, comma 0. So that would be our intercepts there. Okay, so just go through each piece, see if it can equal 0. If it does, you get an x value. Make sure that x value is within the range for that piece. I don't think I should use the term within the interval for that piece, the x value interval. All right, what's next? We got the intercepts. Next, they want us to graph it. So I've set up a little graph here. Oh, a little graph paper. Thought I did that, but I did not. Give me 1 second to get that set up. I can just write it. So remember our function. It's -2x plus 1. That's where x is greater than or equal to -3. Less than 1. It's 2 when x equals 1. And it's x squared when x is greater than 1. Okay. So the first part we can use when we're graphing it is we do know that there is a x-intercept here of 1/2, comma 0. So we do know that. The other thing we do know is that there is, let's go back and look at it, a y-intercept of 0, comma 1, which is here. So we have those 2 points to use so far. The next thing we want to do is look at each piece. So we're going to work away from left to right. So we know that the top part, -2x plus 1, is defined when it's from -3 to 1. And we know that that's a linear graph. It's a line. It's x to the first power. It's the highest degree there. So let's see what it's going to be when x is equal to -3. When x is equal to -3, we're going to use that top piece. It's going to be -2 times -3 plus 1, which would be 6 plus 1, which is 7. So we have the point -3, comma 7, which is going to be up in here. Pop that a little better. There we go. Now we do put a filled in dot there because it can be equal to -3. Okay. We could do some more points. You could do -2. You could do -1. You could do 0. Well, we already got 0. But I want to see what is it going towards. I know it's going to be a line. And I know that line is going to connect to this line, to that point, but it's going to continue, and I'm going to draw it better later. It's going to continue until where X is 1. So what I want to see is, where is this graph approaching as X goes to 1? What is it? What is it in the activity right before it hits 1 and switches over to the next piece of this function? So to do that, I'm going to plug in a 1 in there. So I'm going to do -2 times 1 plus 1. So that's going to be -2 plus 1, which should be -1. So what that's telling me is that top piece is heading towards a y value of -1 when X is 1, but it's not actually equal to it because there's no equal to on that inequality there. So what I'm going to do is put an open circle there. At the point, not drawing it for, there we go. At the point 1, -1. And so that first piece is going to look, and I'll try to draw as best I can. Like that. That is the -2x plus 1. I'll write it. That's that piece. It's that piece from where X is -3, including the -3, up until where X is 1, but not including that 1. So that's why you put the open circle there. All right, let us look at the next piece. Next piece is the easiest. We're going to do it in green. That is just defined as when X is 1, Y is 2. So to do that, just go to where X is 1, Y is 2. That point right there. Boop, 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 boop. So that's the point 1, 2. Oh, really bad one. Fix it up. But that's that piece. And that's all there is to that piece. I don't need to do any type of end activity. What is it going towards? Because it's just 1 point. It's 1, 2. All right. And let's dive into the last piece, which is X squared. All right. So for X squared, it's defined as that for when X is greater than, it should be X is greater than 1 here. Sorry about that. Miscopied it. So we can do some different points. Let's do 2. So if we take 2 and we square it, we'll get 4. So that means we have the point 2, 4. And we could do 3, but 3, 9 is going to be up there. So we'll just do undo that. Now we do want to see what its end activity is. What is it going towards when it is 1? Now it's not going to be a point there. What is it going towards? What is it going to be if it was defined there? And so we'll do 1 squared, which is going to be 1. So we have a point 1, 1 that it would be going towards, but it's not actually equal to. So we're going to put the open circle there, and then this is going to swoop through there and continue on. That's not very good. I would try to draw that again. And there we go. That's heading towards 3, 9. And that's our little quadratic parabola coming off the side there. So this is the graph of a function. Notice it is a function. It doesn't fail. This would be where it would fail the vertical line test, but it doesn't because it's not actually defined on those points. It's open circles, so it's only defined when X is 1 right there. And so this would be our graph. Oh, I guess I should label that. This is the X squared part. This is the just 2 part. All right, the next couple of questions that ask us, let's see. So we graphed it and wants us to find the range of F. So remember, range is your Y values. All right, range is the Y values. Talk about range. We don't have a good way of finding range until we start talking about inverse functions. I'm trying to remember which chapter that is. It might be 6. But we can do it graphically. If we look at the graph here, we can determine what Y values are there. So notice, let's look at the top. So it stops here, but this red line keeps going on and on to infinity. So our highest y value is going to be infinity. This is going up and up and up. Our lowest y value, we're coming up from the bottom. Boom, we hit right here. Now it's not actually defined there, but it gets really close to that -1. So our lowest y value is going to be -1, not including -1. So we're going to put a parenthesis on it. And then it's going to go up to infinity, and we'll close that off with the parenthesis as well. So you use the graph to determine the range. You're just looking for what's the highest y value, what's the lowest y value. Now there may be gaps, and in which case you'd have to union some intervals together to do that. All right, so let's talk about the next thing it's asking us, which is, let's see how they word it before I go. Is f continuous on its domain? So for a function to be continuous, there needs to be no jumps or gaps. Okay. And so basically the easiest way to remember what does continuous mean or continuity mean is, can you draw it without lifting your pen? Okay. So if you can draw the graph without lifting your pen, a continuous function. We do have some jumps and gaps here. Notice right here. I mean, what's happening? It jumps from here to here to here. Or it jump, yeah, I guess it would jump from the blue to the green to the red. That's a major jump going on. You got these gaps in that jump. And so this will not be continuous. This is not a continuous function. So if you have some gaps, that'll be where it's not continuous. What would make it continuous is where these pieces are switching off. I call it the handoff. You're running like a relay race and you're handing off the baton, right? So you're running this race here, then this one hands it off to green and this one hands it off to red. If the handoffs happen and they meet at a point such that there are no gaps. So just as a hypothetical, if this function was defined so where x is 1, y is -1, so that point was right there, and the red part was defined a little bit differently, so it was a quadratic that began at this point and then went off on its way and did what it does, this would be continuous because the handoff is happening with continuity. There's no jump or gap. It's just whoop. There's no jumps or gaps happening between where those functions are handing off to each other. It's just a smooth transition between them all. That would be a continuous piecewise defined function. Okay, and that's it. Be sure to let me know if you have questions on the homework or about anything that we talked about in this video.